Okay, welcome back. This is 1.2, all about linear models and rates of change. A very powerful tool that we will learn is you can kind of take anything and, well, not anything, but a lot of things and turn them into equations, well, kind of do approximations of the things. You know, so here's a curve. We don't know much about this kind of curve. We haven't studied it probably. It kind of looks like a sine curve or maybe something. It's like sine plus x or something. I don't know. But the deal is if you take like a little region like this and zoom in close enough, it kind of looks like a line. If I zoomed in here a lot closer, maybe it looks like this. And then if I zoom in even farther, it's perfectly straight. So I'm looking closer and closer. Maybe I looked in at this region is kind of where I'm looking. Okay, so that notion that we could do these, I don't know, these kind of linear approximations means that all of what we learned about lines are very important. So slope, things like that. We want to go and review all that junk just so we are all on the same page. Okay. So here we go, 1.2, linear models and rates of change. Okay. So the first thing, slope, extremely important to us. We'll start calling slope the derivative here later on. Slope is a term we use particularly though with equations of lines. So we have maybe some points in the plane, x1, y1, or x1, x2, y1, y2. So given these points, x1, y1, and some other point, x2, y2, their slope is given by this formula. Later we'll have these notation here, but it's y2 minus y1 all over x2 minus x1. Okay? And then just as a reminder to you, the sign of the slope tells you whether you're going up or down, right? So this is when you have a positive slope, this is when you have a negative slope. And then, the other, if you had zero slope, you had a horizontal line, and that's kind of important to note as well. And then vertical slope occurs where you have undefined slope, sorry. So this is undefined slope. That's when the line's going up and down. And this should be horizontal. Doesn't look like it, but it is. Okay, so I need to make sure that you know how to find equations of lines given information. And this is kind of a type of question that won't go away anytime soon, because once you get into multivariable calc, you'll look at it in 3 dimensions, and you want equations of planes and equations of lines in space. Right, so it'll come up again. But anyways, we start with point slope form. And you should have this equation memorized. Y minus y1 equals m times x minus x1. So for example, if I give you a set of points on our next quiz, you should be able to generate an equation of a line based off those points. So let's take a look at the slope. 7 minus negative 2 all over 1 minus negative 2 gives you 7 plus 2, 9 all over 1 plus 2 is 3, so the slope is 3. And then we can plug everything into this formula. So I got y, I'll use the positive coordinates. Y minus 7 equals 3 times x minus 1. And then generally we don't want the point slope form. We want the slope intercept form, right? So we're going to solve for y equals 3x minus 3. And so y is 3x plus 4. And that would be your equation, okay? Okay, so lots of story problems in this section, and the key is to kind of identify the points and then go and create your equation of a line. So in particular, I'm looking at this apartment rental problem, which used to exist as problem 79. I'm sure it's still there, but maybe it's moved. So let me find that in my book. I'll be able to tell you exactly where it is at this point. In the new edition, new to be renewed edition. Like that. What section are we in? 1, 2. Sorry. 1 second. Apartment is still 79. It's on page 18. It's saying a real estate office manages an apartment complex of 50 units. When the rent is $780 per month, all 50 units are occupied. However, when the rent is $825, the average number of occupied units drops to 47. Assume the relationship between monthly rent and the demand X is linear. Note the term demand here refers to the number of occupied units. Part A, write a linear equation giving demand X in terms of rent P. So part A, we want to write a demand function. And again, it says we want demand X in terms of rent P. So I want some function X of P. Okay. And in order to produce this guy, I'm going to work with these two points of information. So they're kind of disguised as points. So when the rent is $780 per month, so when we deal with ordered pairs here, because we're writing X in terms of P, the traditional X coordinate will be the P coordinate now. And then where the Y used to be, we're going to write X. Okay, so I need two ordered pairs, P comma X. And in this case, it looks like it's going to be when the rent is $780, all 50 units are occupied. So the demand X is the 50, okay? And then the actual X, the demand is X and the rent is P. So where's our P? The P value, the rent is 780, and then the demand is 50. Okay? And then for the other guy, the rent is 825, and the demand, the output, you can kind of think of it that way, I guess, is 47. It goes down. Okay, so we should expect negative slope for this case, and of course, to find the slope, you just do the y2 minus y1, etc. So I got 47 minus 50 all over 825 minus 780. That'll be negative 1/15 when all is said and done. And then we can go to our point slope formula to generate this equation thereafter. So instead of y minus y1, I have x minus x1. It's a bit annoying, but there it is. And then p minus p1. Okay, so using the first ordered pair I see, x minus 50 equals, the slope is negative 1/15 times p minus 780. I'll distribute this thing, so I'll end up with x minus 50 equals negative 1/15 p plus 780 divided by 15 is 52. Then move the 50 over, and we'll have our formula now in slope-intercept form. So negative 1/15 p plus 102. Okay. Oops, page. Okay, so creating an equation of a line from a given set of points. What else? Let's look at 24. We're modeling data this time. They give you a table. It shows the population in millions of the United States from 2004 to 2009. The variable t represents time in years, with t equals 4 corresponding to the year 2004. Okay, so this is problem 24. They give you a table with time and is the t variable, and y represents the population of the United States. So starting in year 4, which represents the year 2004, and then we're going to go all the way up to year 9. Okay, and then in millions, 293 million, 295.8 million, 298.6 million, 301.6 million, 304.4 million, and 307 million. Okay, so what does the book want? Plot the data by hand, connect the adjacent points with line segments. Okay, we're going to skip that. Let's go ahead and just skip down to part C, I think. So find the average rate of change of the population in the United States from 2004 to 2009. Okay, so what you're doing is kind of approximating rate of change. So note here, what would be the rate of change from 2005 to 2007? Something like that. So from 2005 to 2007, we're asking t equals 5 to t equals 7. Right, so how are we going to write this? It's really a question of slope, right? But it's like, because we're dealing with data points, it's not an exact line. So all you can hope for is kind of an averaging. Okay, so let's look at the slope from that point to that point. So the slope in that case will be 301.6 minus the 295.8, and then it's all over 7 minus 5. Okay. I have to get my calculator for this one. And I'm looking at 2.9. So for that range, the population is going up 2.9 million. Okay, so from you could say you can do an estimate per year and say that the population is increasing by 2.9 million per year. Okay. The book was asking for the average rate of change from 2004 to 2009. So if this was an equation of a line, you would get 2.9 again. Let's see what we're getting here, though. I think it's probably different, right? So again, we're taking these points, first 307, and subtracting away the 293, and then that's all over 9 minus 4. Okay, that'll be, again, I'll go to my calculator. It's 2.8 this time. So you see it's different for different pairs of points. Okay. Okay. So what does this mean? This time the population seems to be increasing by 2.8 million per year. Okay. So it's not a constant rate of change like it would be for a line, but we're kind of approximating this rate of change, and each interval is different. And this is kind of an important point about what we're doing in calculus. We want to get a rate of change for something that's not a line eventually. So this thing, it's almost a line, but not really. Then we could do an approximation, an average for the rate of change. Okay, but later on, it won't even be close to a line, and we'll have to get that concept because rates of change are the language of the universe. Okay, and we are, as calculus students, supposed to be very interested in that. Okay, so anyways, graphing these things. Given the point slope form of y equals mx plus b, what you do is start at the y-intercept, which is 0, comma b, and then you use the slope, which is m, right? All right, so for example 34, we have y equals 1/3 x minus 1. So my y-intercept is 0, -1, and my slope is 1/3, which means it goes up 1 over 3. So I start here. Okay, that's my starting place. 0, -1, it's right here. Go up 1 and then over 3. 1, 2, 3, there it is. Connect the dots, and you are good to go. The second form that you're usually asked to graph will be the standard form. Okay. So on the book, they'll write it ax plus by plus c is 0. And usually what I like to do is just get the x and y intercepts. So problem 38, I have x plus 2y plus 6 is 0. Okay, I'm going to move the 6 to the other side. So I got x plus 2y is -6. Then I'm going to, after my x and y intercepts, for the x-intercept, you let y equal 0. For the y-intercept, you let x equal 0. Okay? And you just make a table, and you can do these in your head. So when y is 0, x is -6. When x is 0, y is -3. Okay, and then we just go over and connect the dots. 1, 2, 3, 4, 5, 6. 0, 1, 2, 3. And there's our line. Okay, we also need to be able to do horizontal and vertical lines. Let's take a look at those real quick. Let's see, horizontal and vertical. So for horizontal lines, that will be where y equals some value, we'll say b. So y is always b, and x varies. So for example, 3y equals 3. Right? So you could simplify this by dividing both sides by 3, and you get y is 1. Right? If you want to do a t-table, then this means y is always 1, and x can vary. And x can be whatever you want it to be. Right? So you come over to your xy plane, get a plot of this, 1 and 2, 1, 0, 1, 1, 2, 1, connect the dots, and you're good to go. The other case then are the vertical lines. And this is the same game. It's saying that x is always some value and y is allowed to vary. So for example, we could have 3x plus 9 is 0. 3x equals -9, so x is -3. And if you did a t-table or a point plotting, x is always -3 and y can vary, right? So -1, 0, 1, whatever. All right, let's go over to the XY plane and plot those. So -1, 2, 3, -1, -3, 0, -3, 1. And we see we get a vertical line like that. Okay. Okay. So hopefully that's a good enough review for this section. And we'll see you next time.